Good morning, everyone. Hope you had a good time at the conference yesterday. So I'm Martin Kleppmann. I'm a researcher at the University of Cambridge, looking into distributed systems and specifically collaboration software. And so I wanted to talk a bit about the work we've been doing in this area. You might know me from this book that I wrote a few years ago. It's called Designing Data-Intensive Applications. The talk today is not really about the same topic as the book. This book is much more about lots of different kinds of databases and systems for data storage and processing, and helping you figure out which systems you might use for which purposes. So which are good and which are bad, depending on the particular type of problem you're trying to solve. So this book is also available in a Russian translation. So if you prefer to read that, that's available here as well. And in fact, there's a stand just outside the hall here where you can get copies of this book as well. So I would like to talk about collaboration in software. And so you are probably all familiar with Google Docs, for example, where you can have several people accessing a document and editing that document at the same time. And I will call this an example of cloud software, or you could call it software as a service or web apps, something like that. The general idea with this sort of software is that you've got the primary copy of the data is stored somewhere on a server. In Google Docs' case, of course, this will be somewhere in Google's data centers. And you access this software maybe through your web browser or maybe through a mobile app, but this kind of cloud software has the characteristic that the primary storage of data and most of the application logic are actually on the server. And the users who access this software from their end-user devices, they have fairly thin clients to access it. And this type of software has worked really well for us over the last 10, 20 years or so. It's very convenient because it means you can access the data from any of your devices. We get amazing real-time collaboration capabilities with this type of cloud software. But there are also a whole bunch of problems. And what we have done recently is to outline a vision for what we think software should look like in the future. And we called this local-first software. The reason for this is that we actually want to try and move the primary copy of the data and the data storage back to users' local devices, so that there might still be servers involved, but the servers just help with copying data from one device to another, but the servers are not necessarily the primary data storage mechanism. So what I'd like to do first of all is just to very quickly outline what we mean with local-first software. For further detail, you can just look at the article at the URL here. And then I will walk through some of the algorithms that we've developed in order to actually build this kind of software. And finally, then I'll talk about some example pieces of software that we've written in this local-first style. So the way we've characterized local-first is through satisfying 7 properties. So these are ideals which we think software really should live up to. But unfortunately, there is no software at the moment that really satisfies all of these. There's lots of software that satisfies some of them, but not everything. So I'll just talk through those quickly, one by one. So the first thing that we want is, it makes sense, we want software to be fast. So we want it to respond quickly. When the user performs some action in the software, we want that to take effect very quickly and not have the user having to wait constantly. And this is a problem here for cloud apps where the application logic is on a server, because it means that if the user enters some data and then maybe clicks the OK button, you have to wait for a round trip to the server for the data to be stored on the server and the response to come back again from the server before you can say, yes, this data has really been stored. And because the speed of light is just inevitably slow, and the speed of the internet is even slower than the speed of light, there is always going to be some delay while you talk to a server that might be located on a different continent. Now, we can do tricks to try and hide this kind of latency, and what is popular amongst JavaScript web application developers these days is a pattern that is called optimistic UI, optimistic user interface, which is essentially where we say that, okay, when the user enters some data and presses the OK button, we just immediately show the user interface as if the data had been stored to the server, even though actually the communication with the server is happening asynchronously in the background. And so this now makes the software feel much faster for the user, but it has the problem that if anything goes wrong, maybe the server returns an error message, or maybe your internet connection is unstable temporarily, and so the communication with the server is interrupted, then you have to later update the UI and saying, oh, actually, sorry, we said the data was stored, but actually it hasn't been stored yet after all. So the mental model here becomes rather confusing. What we can do instead, what we're advocating with local first software, is that actually we make the data storage on your own device the primary copy of the data. This is kind of seems obvious, but it has the very nice property that you can change some data without waiting for any network round trip, because you can just store it locally, which is always very fast, and then sometime later in the background that data can be synchronized with a server, and it can be synchronized with any other users. And so we can just, by using the local data storage, we can get better performance. However, if you only store the data on a local device, that's very inconvenient, because nowadays with software we want to be able to access it from multiple devices. This is, again, pretty obvious that we want this. We want to access our own data not just from our phone, but also from a tablet and from a desktop computer and maybe even more devices. So this means we might be using local data storage on each of these devices, but we do need to synchronize that data across all of these different devices. Another thing that we want to be able to do is to work offline. This is something that a lot of cloud software is really bad at. But if we're storing data on the local device, it's actually no problem, because you can just keep editing some document and it will be stored on your local disk. And then at some point later, when you have an internet connection again, then you can perform your synchronization with servers or with other devices. And I think being able to work offline is very useful, even though nowadays we often have Wi-Fi, we're often in places where we do have internet access, but this is not always the case. Maybe you're sitting on an aeroplane where there's maybe no in-flight Wi-Fi, maybe you're on a train going through a tunnel, maybe you're just in a very rural area where cellular data coverage is thin, maybe you're traveling in a country where cellular data is available, but roaming is very expensive. So there are lots of reasons why you might be disconnected from the internet for a while, and really you should be able to continue doing your work even if you're disconnected. So unfortunately, a lot of software handles this really badly. This is Figma, for example. There's a piece of desktop software, but the software is actually just a little wrapper around a web view, and so without an internet connection, unfortunately, this software cannot do anything at all. Or with Google Docs, you might have experienced this. You might be happily typing along in a document, and then your Wi-Fi cuts out for just a minute, and Google Docs then turns your document into a read-only document. So you were typing, and suddenly the document is no longer accepting your keyboard input because it has decided to go read-only. Unless you install some extra extension that is supposed to enable offline support, but it unfortunately doesn't work very well. So again, working offline is another thing that we want from local first software. The fourth thing we want is collaboration. And so this is an area in which things like Google Docs, they really shine. And so Google Docs has showed how amazing it is if several people can edit a document at the same time without having to send it back and forth by email. So that's what you're most familiar with there is this kind of real-time collaboration where every single character that you type in a document is immediately sent to the other collaborators. And so you can really see the other people typing letter by letter. I'll call that real-time collaboration. But there are other forms of collaboration that are also very useful. So you could have a more asynchronous form of collaboration, which Google Docs, for example, will support in the form of suggestions. So you can have, rather than applying your edits immediately to the document, you could put it into suggestion mode, and then any change you want to make will appear like here as a box on the side, and the owner of the document can then choose whether to accept or reject those changes. And so this is just, it's also a very built-in form of collaboration in the software, which is also very useful. You might also be familiar with Git, which is also a model for collaboration. It's very different from Google Docs, but it has this mechanism called pull requests if you use something like GitHub. And that also is a form of asynchronous collaboration where one user can suggest some changes to a code base and somebody else can review it and then accept whether to merge, decide whether to merge that pull request. The trouble, however, which you will have probably experienced with this type of collaboration is that you can get conflicts. And so with Git, merge conflicts can look fairly horrible. This is an example of a merge conflict I had a little while ago. And resolving these things is rather tedious, especially if people have made a lot of changes to similar parts of the code. So you get these tools here, this is called diff merge. It's a tool for three-way merging of code. There are lots of other tools which also have to handle conflicts in some way or another. Conflicts can arise because two different people have edited the same piece of data on different devices. So the same happens with Dropbox, for example. In Dropbox, you can have some document being edited on one computer and on a different computer, maybe by different people. And in that case, Dropbox doesn't even attempt to merge those. It will simply give you these conflicted copy files and tell you to sort out the merge yourself. And this is, in a way, inevitable in the case of Dropbox, because Dropbox treats files just as byte streams. It doesn't try to interpret the contents of the files in any way. And so because the files might not just be text files like in Git, but the files might be spreadsheets or they might be graphics documents. And so really Dropbox doesn't want to get into the business of merging those things, which is understandable, but it also means the user experience for collaboration is terrible if several people update the same file. Another terrible example is Evernote. You might have tried here with Evernote, you can write notes, you can edit those notes on different devices, for example, on your phone and on your desktop. And if that does happen, Evernote will just like dump a copy of the note in this separate notebook called conflicting changes, and again, leave it to the user to sort out this merge. So it really doesn't help at all here. So what we want of local first software is to have several people being able to edit the same files at the same time concurrently and to handle the merges in a nice way. And this is the main thing I will be talking about later on in the talk when we go into some algorithms for doing this kind of collaboration and merging. Another thing that we want of local first software is to improve the long-term preservation of data. So this is a bit more an idealistic point of view. If you think back at the software we used to have in the 1980s, 1990s, running on DOS or Amiga software or so, this software still exists, and the Internet Archive has done an excellent job of actually building up a library of this old software, and the software will actually run in an emulator in your web browser, because it's just like 2 megabyte download or something like that. It's very quick to download and run nowadays, and it can all be emulated in JavaScript. And so this is amazing because it means this generation of past software, even though we don't actively use this 1980s software very much nowadays, it's still there, it's still preserved, it's part of our intellectual heritage. If you compare this with a lot of cloud software, unfortunately, if it's a web app and if the server is not open source, if the owner of the software decides to shut it down, and software does get shut down quite a lot, it simply disappears. So the Internet Archive has no ability to archive copies of Google's products that Google has shut down over the years because they just run somewhere on a server. There's nothing that the Internet Archive can download and preserve and run in an emulator, because here with web apps, they fundamentally defy attempts to preserve it. And so sometimes software just gets shut down. This is especially the case if the software is developed by a startup that might just run out of money anytime. Or sometimes just data gets lost by cloud service due to incompetence, like MySpace a few months ago just losing a huge chunk of the music heritage from the particular period of time when MySpace was popular. This is really sad because we are really losing a lot of the data that is being created nowadays, and historians in the future will look back at our time and simply will not know what was going on because they won't be able to access the data that we created nowadays because it's all stuck in some piece of cloud software. If you compare this with writing from 5,000 years ago from the Sumerian culture, this clay tablet is still readable and has been preserved over an incredibly long time. And a lot of computer software is unfortunately not like this. So one of the things we would like of local first software is to actually make it easier to preserve data long term. And storing the data on your local device is part of that story. So that hopefully that data we can still make that data readable in 20 years' time or in 100 years' time. So another point of local first software is that we can improve the security model. So in typical cloud software, you've got encryption between your end user device and the server so that communication goes over HTTPS. It's encrypted with TLS typically. But once you reach the data center, everything is unencrypted again. And so that means you have to fully trust the data center. And one thing we can do with the algorithms that we've been developing is to actually move to end-to-end encryption, where the data that is stored on any servers is still encrypted in a way that the servers cannot read. And so this gives us much better security properties because we don't have to trust the operators of the servers as much anymore. So that was a very quick overview of what we think of as local first software. And what I'd like to do now is to run through some techniques for actually realizing these goals. So there are lots of existing software projects that satisfy some of them. So I talked about Git, for example, or Dropbox. They actually have very nice properties in the sense that, you can work with your files offline, you can preserve those files long-term very well. There's really good user control over those files. But, for example, in the case of Dropbox, the collaboration is terrible. On the other hand, you have web apps, which are the total opposite. Like, web apps can enable amazing collaboration, but the offline editing story is typically terrible. So really what we would like to do is to try and develop technologies that get 7 green check marks on this big table here. So the big part that we need to solve for that is actually enabling collaboration. And so especially collaboration in the setting where the primary copy of the data is stored on users' own devices. So let's take a text editor as an example. In a text editor, you can have 2 users, and they both start off with the same document that says hello. And now, say, the red user edits this document to insert the word world before the exclamation mark. So we have hello world exclamation mark. And concurrently, the blue user inserts a smiley face after the exclamation mark. And so these 2 edits happen concurrently. They might even happen offline. They happen without knowledge of each other. And then at some later point in time, these users exchange their edits, and then we want those changes to be merged together into a consistent document. And in this case, the merge is fairly clear what we would want. We, of course, want to keep the word world before the exclamation mark, and we want to keep the smiley after the exclamation mark. So these edits can be merged together in a nice, reasonable way. And what we want is that eventually everyone ends up in a consistent state, which is known generally in distributed systems as eventual consistency. However, eventual consistency is very imprecise in the way that it's defined. So typically the way eventual consistency is defined is whenever people stop writing to the database or stop updating their documents, then eventually everybody will see the same state. And there are a number of problems with this. For example, what happens if people never stop editing? Then this statement says nothing about what sort of state they might reach. Also, it doesn't say anything about what that final state should be. Is it okay to simply delete the entire document for everybody? That would be a consistent state, but it would not be very useful software. So what we want to do is to break down eventual consistency into some more precise properties, first of all. And the first of these is, rather than talking about eventual consistency, we can talk about eventual delivery of messages or edits. And that is that if one user makes an edit to their document, then eventually a message representing that edit will be received by another node, by every other node that has not failed. And so we're not making any timing assumptions here. In terms of timing, if both users are online at the same time, then the edit might reach the other user within 100 milliseconds. But if users are editing their document offline, and they are offline for a week, and only after a week they come back online again, this looks very much like network delay, where the delay happens to be a week, and that is okay. So we're allowing arbitrarily long delay for messages to be delivered, as long as they do eventually arrive. And then we can require convergence. And convergence is defined in this way, that if you have two nodes or two users, and they have seen the same set of operations, then they must be in the same state. So this holds even if they saw the operations in a different order. So this means now we can achieve eventual consistency by first having eventual delivery, that is, we make sure that all of the messages eventually get through, and then for any two users who have the same set of messages, then they will be in the same state. And so that means as users exchange messages, they will converge towards the same state. And finally, we have to require that we don't lose any data, because otherwise the trivial solution is possible where we just throw away things. That would not be very useful. So these three requirements we need in order to have a sensible definition of what it means for users to end up in a consistent state. And there are two families of algorithms that have been developed in order to achieve this kind of thing. So you might have heard of operational transformation, which is the algorithm used in Google Docs for the real-time collaboration. Operational transformation was first developed in the late 1980s, and it had a lot of problems, unfortunately. So it works quite well in the setting where you make all of your edits through a central server, where there's a server that acts as a conduit for all of the messages. So whenever any edits get made, they have to be first sent to the server, and then the server forwards them to the other collaborators. And if you're willing to assume that, then operational transformation can work quite well. Operational transformation does not generally work in the case where you have peer-to-peer communication. And so for this setting, conflict-free replicated data types were developed. They are called CRDTs for short, and CRDTs is our main area of research. So this is what I'm going to be mostly talking about today. So what I mean with peer-to-peer, as I mentioned just now, is essentially having a choice of different communication mechanisms. So let's say we have Alice and Bob want to collaborate on some document. And the way this communication works in the case of Google Docs is Alice makes an edit. That edit is sent over HTTPS to some server operated by Google. And then Bob also connects to that server, and the server forwards the edit along to Bob. And the server actually does a bit of work along the way to transform the messages in order to handle the concurrency that might happen between these two users. And this is the way cloud software is typically built, right? So the communication goes via a server. But for local first software, it would be really nice to have other options for communication. Because if somebody shuts down that server, the software will no longer work. You can no longer collaborate. So can we make this kind of software work even without a server? So for example, if Alice and Bob happen to be on the same local Wi-Fi, because maybe they are colleagues in the same company, we could just send the edits directly over the local Wi-Fi network without ever going via the internet. So just using the local infrastructure. And really, this should be possible. I think it's ridiculous that we should send all of our edits via a server on a different continent if we could just send it over the local Wi-Fi. Now, the local Wi-Fi will not be enough if you've got two people in remote locations, But in that case, we could use a peer-to-peer network to connect these two users to each other directly. On the other hand, if the users are very close together, or the devices are very close together, you might even be able to use Bluetooth as yet another communication mechanism. Especially just if it's synchronizing between your phone and your laptop, they're right next to each other. It's ridiculous to send the edits via a server somewhere remotely. We should be able to just use the local Bluetooth. Now, thinking even more widely about different communication mechanisms, one of the things I've been thinking about is, say we wanted to build a medical record system for use in rural Africa, where we cannot assume that there's reliable Wi-Fi or cellular data coverage. And so in this kind of setting, say the nurse in the village wants to update a medical record and send it along to the hospital in the city. And in this case, how do we make that kind of communication work? And it might be that the best way of establishing this communication between the village and the city might be to store the data on a USB stick, on a USB drive, put it in the pocket of a guy, put the guy on a motorbike, then the guy drives from the village into the city, plugs the USB stick in there, and transfers the data this way. And this is a very high latency form of communication, but also fairly high bandwidth, and it might actually be a reasonable thing to do in certain settings. So the moral of this story, what I'm trying to say here is just we want to be able to use any kind of communication mechanism that happens to be available or appropriate. We don't want to have to make any assumptions that all the communication goes via a server, because there's so many other forms of communication that don't go via a server and that are really useful in some settings. And so this is how we can move towards local-first software and make our software better. We can reduce our dependency on servers by firstly encrypting any data that we store on the servers, and secondly, allowing communication mechanisms that don't use servers at all, but actually just go directly between the peers. And CRDTs allow collaboration in this kind of setting. So this is the biggest difference between operational transformation and CRDTs. CRDTs give us the freedom to use any of these communication mechanisms because they make no assumptions about the network topology. However, I said earlier that operational transformation has had a bunch of problems in the past. So people have tried to build operational transformation algorithms for peer-to-peer networks, and unfortunately many of those algorithms were simply wrong. So they looked plausible if you looked at it on paper, but actually they have certain edge cases in which they simply remain permanently inconsistent. And we wanted to be very careful that we wouldn't repeat those kind of mistakes. And so we went into some efforts to do formal verification of these algorithms in order to really prove mathematically that they really do converge under all circumstances, no matter how messages might get delayed or reordered or duplicated or lost in the network. No matter how the timing happens to work out, we want to make sure that we will always be guaranteed convergence. And so for this, we did some work about 2 years ago where we took a bunch of CRDTs, so RGA and ORSet and so on, those are examples of CRDT algorithms, and we proved that they satisfy a particular consistency model called strong eventual consistency. This consistency model essentially requires convergence. And we did this proof using a piece of software, a proof assistant called Isabel. And so this means it was not just a pen and paper proof, which we would check by hand, but actually the software is checking the proof for us to make sure we cannot make any mistakes in the reasoning. And we proved that these algorithms satisfy strong eventual consistency under certain assumptions. But these assumptions, that's where things get dangerous. Because if we make an assumption that is not true, then the entire proof is useless. So in order to make sure that we didn't make any wrong assumptions, we then also introduced a model of a network that describes exactly how the network may lose or reorder or otherwise mess around with messages. And we were able to prove that these assumptions from the first step of the proof, those assumptions hold under all possible executions of the network. So no matter what the network ends up doing with us, in absolutely all circumstances, we will be able to satisfy the assumptions, and therefore we will achieve strong eventual consistency. So I don't have time really to talk about the proof in great detail, So I've just put the URL up there if you want to read the paper, which describes it in quite a readable way. What I want to talk about instead is some concrete examples of collaboration and merging of states to give you a bit of a feeling for how these algorithms actually work in practice. So let's take this as an example. Let's imagine we have a to-do list application, and we can represent the state of our to-do list as a JSON document. So I'm just going to have a list of to-do items, and in this case there's one item in the to-do list whose title is watering the plants, and it has a Boolean field which indicates whether the checkmark box has been pressed or not. And so in this case, it has not been pressed yet, so the done field is set to false. And now, imagine this to-do list is shared between multiple users who might update this document, this to-do list, independently. So for example, on the left-hand side, we could have a user who updates the to-do list by inserting a new item. So the new item is buying milk. It's also not done yet. And here this to-dos.push, the push method is just a JavaScript method for adding a new item to the end of an array. And so on the left-hand side, we add watering the plants as an item. On the right-hand side, we update the first item in the to-do list and set its done property from false to true. And so as we apply both of these updates, on the left-hand side, we now have a to-do list containing 2 items. On the right-hand side, we have a to-do list containing only 1 item, but its done field has been set to true. And now, these 2 concurrent edits we want to merge together. And in this case, the merge that we want to do is pretty clear, I think. We want to preserve both these changes that have happened. So that means as the network communication happens, on the right-hand side, we end up with buying milk being inserted as the second item. On the left-hand side, we end up with the done true for the first item being applied. And so in this case, it's quite clear what we would want, and I think this, hopefully everyone would agree that this is a reasonable way of merging these concurrent changes. So that's one example. Another example might be text editing. That's the example we had earlier, in fact. So we had the example where it was hello. On the left-hand side, someone inserts the word world. On the right-hand side, someone inserts the smiley face. And so we can do that here again by calling this method .insertAt in order to insert text at a particular position in the document. And so again, we end up with 2 divergent versions of the state, and as communication happens, we want to merge them together into a consistent state. So this is exactly like the example was earlier, and in a minute I will show some algorithms that actually achieve exactly this kind of merging behavior. One more example of concurrent updates. Let's say we want to add a deadline to an item in the to-do list. So this is just when the reminder is going to pop up to tell you that you wanted to do this by a certain date. And so on the left-hand side, the user updates the deadline for the first to-do item to be the 10th of July. And on the right-hand side, another user updates the deadline for the same item to be the 14th of July. So now left, you have 10th of July, right, you have 14th of July. How do we merge these now? So it makes no sense to concatenate them in any way, because that would not be a valid timestamp then. We could just pick one of the 2, but then how should we know which one we should pick? Because we don't really want to discard any user input. We don't want to lose anything. But we can't really sensibly merge the values either. And so in this case, what we can do is we can keep both of the values that were written. We could pick one of them as like being the default resolution. And so in this case, for example, maybe the 10th of July gets picked as the default, but the other value, the 14th of July, is still there as a conflict value on the side. And so if the application wants, it can now show some user interface to the user saying, oh, sorry, there were conflicting updates for this particular value. Do you want to pick one of the 2? Or maybe the application has some kind of policy for resolving this. Maybe it'll say, we always picked a sooner deadline, or always picked a later deadline, or something like that. But it turns out that actually this case here is the only case in which we have to do the merging manually. So the only case where this manual merging of conflicts happens is when several users concurrently update the same property of the same object. Or alternatively, they update the same item, the same position in the same list object. But this is the only one case in which we actually end up with these conflicts. For all other kinds of edits, that is, inserting or removing items from lists, updating, adding new fields to objects, for example, all of those things can actually be merged automatically. So let me give you a bit of a flavor for how these algorithms work. There are different ways you could implement them, but I'll talk about the ideas behind our implementation. We've got a JavaScript implementation of these data structures that is called Automerge, which I will show you some examples of that later. I'll just talk about the algorithms first. And the basic principle is that any changes that get made, we break down into operations. And the operations are just a precise description of exactly the change that happened. And those operations are then also what gets sent over the network to other users so that they can apply the changes on their own copy of the data. So the operations are our mechanism for synchronizing data. And the operations need to contain a bit of additional metadata so that we know exactly how the changes should be applied. So for example, if we create a new item in the to-do list, here we have an object. It's a map object, that is, it maps keys to values. The first key is title, and it's mapped to the value watering the plants. The second key is done, and it's mapped to the value false. And we can construct this object here with 3 operations, and those 3 operations I've written down here in this JSON notation. So the first operation creates a map object, and we will just associate a unique ID with that object. And so here, I'm just going to call it 1A. This 1A is the identifier that uniquely identifies this particular map object. So think of it a bit like a pointer, except that it works across many different devices. So it's not limited to a single address space, but this ID is the same across any device that has a copy of this document. And then, now that we created this map object, we can create 2 properties, or 2 fields, within that object. So we can create, first of all, a title field, and set its value to watering the plants. And second, we create a done field, and set its value to true. And for both of these, we associate it with the object 1A. So that is our way of saying, which object are we updating to add this field here? Well, we're updating the object with ID 1A. So first of all, make map constructed that empty object, and now we create those 2 fields within it. And for each of these 2 operations, we actually associate an identifier with them as well. So here the 2A and 3A are the identifiers of the unique identifiers of those 2 assignments of fields. And now, when we later come on and want to update one of those fields, that's again just an operation, and we just add the operation to the set of operations. So for now, just assume that we never actually throw away any operations, we just keep collecting them and keep accumulating, and this allows us to actually see the edit history of a document as well. And so here, when we want to update an item done from false to true, we construct a new operation. We give that operation ID of 4A. We are updating the object 1A as before, and within this operation, we are updating the key done, and we're setting it to the value true. And so here, this updates it. Finally, notice here right at the end, we overwrite the assignment, the prior assignment of the field with the ID 3A. So 3A was the ID of the assignment where we set done to false, and here by saying that the assignment of true overwrites the prior assignment with an ID of 3A, we're saying that the value true replaces the value false. This is how we know that these 2 operations, one depends on the other, one invalidates the other, effectively. So this allows us here to see that the value true overwrites the value false in this object. If you compare this to the example of the deadlines, so we have 2 deadlines being set concurrently, one as we had before, one to the 10th of July, the other to the 14th of July. And in this case, we have 2 operations, so, We have two operations, one with an ID of 5a. Again, we're updating object 1a, we're setting the key deadline to a value. And the other operation, in this case, has an ID of 5b. We're updating the same object and the same key, and we've got a different value. Notice here that neither of the two operations overwrites the other. So they simply have two different IDs, neither of them overwrites anything, and this is how we know that these are two conflicting values, because we know that they happened concurrently because neither of them overwrote the other. And so this is a very simple mechanism here. Just by keeping track of these unique IDs for operations, we can see exactly what are the dependencies between them, what overwrites which, and therefore we can figure out exactly what the value of this field needs to be at any given point in time. So I said we would talk a bit about text editing and how to implement that. This is quite an interesting algorithm, so I'll go through that in a little bit of detail. In this case, let's say we start off with a text document containing the letters H-E-L-O, so hello with one L. And let's say, again, we have two nodes, a node A on the left, node B on the right. And we're going to have two users update those documents concurrently. So on the left-hand side, we insert the letter L, and on the right-hand side, we insert an exclamation mark, in this case, in this example. So the way we're going to do this now is, again, we're going to use unique IDs, like for the operations we had earlier. And in this case, we're in fact going to give a unique ID to every single character, to every single letter in the document. And so here we start off, when we start off and we look at the initial document, we've got the letter H has an ID of 0A, the letter E has an ID of 1A, letter L has an ID of 2A, and so on. And those IDs are the same on both copies of this document. And so now when we insert a character, again, we give that character a unique ID. And we're going to generate this ID in a very particular way. And so you've noticed here maybe the IDs consist of a number and a letter. And we're going to choose them as follows. For the number, we look at all of the existing IDs that we've ever seen, and we pick a number that is one greater than the greatest number we have so far. So in this case, we start off with a document containing numbers 0 to 3. And so when we generate a new ID, we will give it a number of 4, because 4 is one greater than the greatest number we've seen so far, which is 3. So that is the number part. Then for the letter part, the letter is going to be the unique identifier of the node that actually produced this operation. And so we're going to assume here that each node has some unique identifier, and that might be just a long UUID, or it might be the hash of a public key if it's a cryptographic protocol. It might be some manually assigned ID. It doesn't really matter. It just needs to be unique. And so what we have now here is the combination of a number, which is a counter essentially, and this ID of the node, which is here a letter in this example. And the combination of those two is globally unique. And so this is actually called a Lamport timestamp. Leslie, I don't know if you're in the room, but your work from 1978 is still going strong. And so these timestamps here, they're not timestamps of a clock, really. They're just counters that get incremented. But they are globally unique because the node ID is globally unique. And then within the operations generated by each node, the number part is going to be unique. But here, the number part can be the same across two operations generated by different nodes. So on the left-hand side, we generate an ID of 4A. On the right-hand side, an ID of 4B. Because, again, we pick one greater than the greatest number we have so far, which is 4. And B is the name of the node that produced the insertion of the exclamation mark here. So now that we've got those two operations, we can send them to each other. So the two collaborators send over some kind of network, send each other these insertion operations. And we can say that on the left-hand side, the left-hand user wants to insert the letter L. That letter has got the new ID of 4A, and we're going to say we're going to insert that letter after the existing element with an ID of 2A. So that is 2A is the first L, so we're going to insert the second L directly after the first L. And on the other hand side, we've got the insertion of the exclamation mark, we're going to give that insertion a unique ID of 4b, and we're going to insert it after 3a. So 3a is the letter O in hello. We're going to insert the exclamation mark after the O. And so the network can now deliver those messages to the other node where we apply those. And so on the right-hand side, for example, here, we take the insertion of L that was generated on the left-hand side, we apply that. And this works like you would expect. So inserting L with ID 4a after 2a. So 2a is the first L. So we put the new L with the new ID after the first L. So we end up with hello exclamation mark like we would expect. And in the other direction, similarly, we take this insertion of the exclamation mark with ID 4b after 3a. So insertion of exclamation mark with 4b after 3a. 3a is the O, so we put the exclamation mark after the O, and we end up with both users being in the same state, which is exactly what we wanted. So far this is fine. You might be wondering, what happens if two people want to insert text at the same place in the document? And so for that, this is where the algorithm actually gets interesting. So let's say, again, we start off with a document ABC, and A has an ID of 1A, B has an ID of 2A, and so on. And on the left-hand side, we're going to insert XY between the A and the B. And like before, we're going to give each insertion an ID, a unique ID. In this case, the insertion of X gets 4A, the insertion of Y gets 5A. And on the right-hand side, we're going to insert PQ, and we're going to also insert the PQ between the A and the B. And so here again, we generate IDs in the same way. The IDs are 4b and 5b. Now, what happens when these operations get propagated to each other? Let's start first with the PQ on the right-hand side. So let's say the insertion of P gets sent over to the left-hand side. And so here we're inserting P with a new ID of 4b after 1a. So 1a is the letter A. 1a is the letter A, so we're inserting the letter P after 1a in the place where we expect it to be. So this means we end up here with the P in between the A and the X. And then similarly for the letter Q is inserted after 4b. 4b is the letter P, so that means we put the Q here directly after the P. So our final state here on the left-hand side is A, PQ, XY, BC. Now, as we go in the opposite direction, we need to make sure that everybody ends up in a consistent state. So how do we do this? Now, we want to take this insertion of X from the left-hand side, this insertion of X up here, it's given a new ID of 4a, we put it after 1a. But notice now here, if we put the X directly after 1a, then we would end up with the text saying AXPQ, which would not match the left-hand side, because on the left-hand side we've got the PQ before the X. So we have to make sure that on this hand side, the PQ also comes before the X, or the X goes after the PQ. So this is the key moment. And the way we can ensure that is as follows. We have one additional rule, and that is we look at the ID of the incoming operation. So here the incoming operation is the insertion of X, and so this operation has an ID of 4a. And first of all, we say, okay, 4a is inserted after 1a. 1a is the letter A down here. We're going to first of all find that position. So we're going to think about putting the X directly after the A. But now we're going to compare the ID of the incoming operation, which is 4a, with the ID of the character 1 to the right, the character directly to the right of our insertion position. So we want to insert after the letter A, so we look at the character to the right, which is the P in this case, and this P has an ID of 4b. And now the rule is we're going to skip over this character if the ID of the existing character is greater than the ID of the incoming character. So in this case, the existing character has an ID of 4b, and the incoming character has an ID of 4a. So we first compare the numbers. The numbers are the same. In that case, we go back to comparing the letters. In this case, we say B is greater than A, and so the existing character P with an ID of 4b has a greater ID than the incoming with an ID of 4a. And so we're going to skip over the 4b character. Then we look at the next item to the right. So here we have 5b as the ID. 5b is even more greater than 4a, because here we just compare the numbers. 5 is greater than 4. So we skip over this one as well. So we skip over the q. Next, we compare to the letter b. The letter b has an ID of 2a. 2a is less than 4a. And so we don't skip over this one. So our rule is we skip over any IDs that are greater, and we stop when we reach the position when the IDs are smaller. And it turns out that this does, in fact, ensure that everybody always ends up in a consistent state. It's not entirely obvious that this is always the case, but that's why we did the proofs that I talked about earlier, so that we can guarantee that everyone really does end up in the same state in all circumstances. So this was the difficult one. Now there's just the letter y remaining. Letter y is easy now, because letter y is just an insertion with ID 5a after 4a. 4a is our letter x, so we put the y directly after the letter x, and everything is fine. So the last thing to check here would be that the skipping behavior never happens in other cases, and you can go through all of the cases here, and you can see, for example, here that on the left-hand side, this insertion of p here, that would not skip over the x, because 4b is greater than 4a, so the insertion of p will not skip over the x, and so the p will be before the x here, just like the p is before the x here. And so this ensures that everyone ends up in a consistent state. So this algorithm it's called RGA, or various variants of this algorithm have also been proposed, but it's quite a nice algorithm, and I hope you find it as interesting as I do. So in terms of how this now looks in terms of the operations we send, we could have, again, our API, for example, that here says we want to insert an exclamation mark into the text, and we can turn this into an insertion operation where we say, we give some unique ID to that insertion operation, we say it's after some existing operation, and we give it a value, okay? So this is now looking quite familiar again. You might be wondering what happens if we want to delete items from the text. In this case, we can't really fully delete the item from the data structure because, remember, we're using these IDs here to identify positions in this sequence of characters. And so we have to remember where a position is, even if the corresponding character is deleted. So we can actually make a removal operation and say that this removes the prior inserted value with a particular ID. So again, like earlier with the overwriting, we've got a reference from one operation's ID to another operation's ID. And in this case here, we will remember that 3a is in a certain place, but we will effectively mark that item as deleted. So it's never actually removed, but we just mark it as deleted, and therefore it doesn't appear in the visible document anymore. One last item. So this is we could have a new item being inserted into the top of a list, say watering the plants is inserted. .unshift is again the JavaScript method for adding a new item to the beginning of a list. And again, we can do that with an insertion. So if we're inserting here at the beginning, we can represent that insertion at the beginning by saying we insert after head. A head is just a special value saying right at the beginning. And now we could even consider moving items around. So you might drag and drop items in a to-do list to reorder them. And so this, again, we could express by having an insertion operation which says this is the new place where we want to move a list item to. And we're going to say what is the item we want to move by, again, referencing its ID like we did previously. And this is a mechanism how we actually can implement reordering and drag and drop on these kind of lists. So that was a very quick overview of conceptually how these algorithms work. We've actually implemented these things as well. So our JavaScript implementation of these ideas is called Automerge. And they developed this together in collaboration with some folks called Ink and Switch, a research lab. And Automerge is a library of data structures that is designed for building these kind of collaborative, local-first software applications. You can build various different applications on top of it, And we've built a couple of examples. So for example, we built an application called Trellis, which is a clone of Trello, the project management tool. It looks a bit like Trello, that is, you've got cards and columns, and you can assign those cards to people, the cards representing tasks. You can drag and drop them between the columns in order to move them around. And we can implement this on CRDTs using exactly the kind of algorithms that I just talked about. Another example of an application we built, we call Pixel Pusher. It's a simple graphics application, a sort of retro gaming style pixel art application. This was actually an existing piece of software, an existing single-user piece of software that we found on the internet, open source, built by someone called Javier Valencia. And we took this single-user piece of software, ripped out the data model in the middle of the software, replaced it with Automerge, and now we have multi-user software. So this was our experiment of adapting single-user software to become multi-user collaborative, and it actually worked pretty well. Another example we built was Pushpin, which is a kind of 2D canvas in which you can import pictures and PDFs and web pages and text and so on. You can move them around as a way of organizing your thoughts and ideas. And we built a tablet app also. This one is called Capstone, where you have handwriting input. And again, all of the input here is represented as CRDTs, and it's synchronized across multiple devices, so it's collaborative. You can have several people editing. It works offline, and so on. It satisfies a lot of those local first properties we were talking about earlier. Now, you can also run Automerge on top of various different networking stacks. So like I was saying earlier, it doesn't have to go via a server. You could go via WebRTC, for example, and Trellis used a WebRTC-based communication. You could also go via different peer-to-peer networks. We've done some experiments with the DAT project and built Hypermerge, which is the combination of Automerge with Hypercore, which is part of the DAT project. This is just an existing peer-to-peer communication library, and we can run our collaboration on top of that. Or, of course, if you prefer, you can go via a server as well, a WebSocket server, for example. So this was a very quick overview of all of the things we've been exploring in this area. If you want to know any more of them, here's a bunch of links. So all of the software I mentioned is open source, and you can have a play around with it if you like. There are a couple of articles here as well. So our local first article outlining our vision for how we think software should be like in the future. At the bottom here, we've got our article on formal verification of these algorithms. We've also got a somewhat theoretical article on how to represent JSON in CRDTs. And yes, various open source code, as I mentioned. Just the last thing I should mention is that my book is available if you're interested from the stall outside, and I will be doing a book signing immediately after this talk in the discussion zone 1, so that's just on the left as you leave the room. So thank you very much. I think we have only time for 1 or 2 questions, since I had a lot of material I want to cover, but I hope you found that interesting. And yes, please, let's have some questions. Thank you.
So, my colleague told me that we have just 2 minutes for one question here, and all questions you want to ask Martin, you can ask him in discussion zone next. So, one question. It was first.
Hello, Martin. Thank you very much. And the question is, what if 2 users edit the same data, and we decide for them what the data in which order or which data would rewrite each other? So, do we tolerate the user's meaning in this case?
So I'm not sure I totally understand. Was the question how you order the edits if several people edit?
Such ordering, does it tolerate the user's meaning, the user's feelings?
Maybe we should talk afterwards so that I can hear you better. It's a bit difficult to hear in here, sorry. So yes, I'll be over in the discussion zone. I think that will probably be the best.